here. So here's some questions I want you guys to see whether you are able to answer them. The first question is the following. I have the operators, so I'm going to erase this part now. So erase this part, so that way you will be able to see whether the question number one. So here we have operators Lz, Lx, and Ly, like these. So here's a question for you. Which two are commutable? Did you have four operators? Which two are commutable? Tobin.
X and Y.
Okay, so is this correct, Alex? X, Y commutable?
No. It's the L squared and then
It should be L squared, and what's the here?
LX.
Lx. Yes, this is commutable. Make sense? So what about this, Cody? What about Lx, I, Ly equals what? Alex, can you help? Lx, Ly. Okay. Aisha, can you help?
It's IH, LZ.
Exactly, you got it. Did you guys remember? So you was X, Y, Z like this. Always remember X, Y, Z, okay? So in other words, if I have Lx, Ly, you will have Lz. And then what about the Tobin, what about this? Equals what?
IH bar LX.
Exactly, you got it. You got it. So that's, and these are commutable in this case. So you guys passed the first question. That's very good. Okay, so the second question, the eigenfunction of L squared. What we call this eigenfunction of L squared? Cody, what do we call the eigenfunction of L squared? So that was L squared eigenfunction. Alex, you remember what's the eigenfunction we call this? Okay, look at the board. Look at the board. What we have here? What we have here? Did you see it? Did you see it? Did everyone see it? So this is called spherical harmonics. Okay, you got it? So that must be spherical harmonics. So this is the spherical harmonics, and we're writing this following way. Y, Ln. So that's the spherical harmonics. You must remember these ones, though, because that will quiz you on that. Okay, so that's very good. And that's all the questions that I have. So just to remember, these commutation relations are very, very important, and we will utilize quite frequently. And I want to show you 100% problem will be in the Wednesday's quiz. Either this one or this one will be on Wednesday's quiz. So I want you to prove this equals I, Lz, and this one will be 100%. So essentially each one, maybe one of them, maybe both, so they will be on that. And there's nothing else that I will more important than this. So this is the one that I will quiz you on. And so let's get started. Today our task a little bit heavier than previously. And so I want to remind you where we finished, and then we will show you what we are going to do. So what we did last time, the spherical harmonics from the page 106, and we already figured out the eta part, which is the eigenfunction of Lz. So the eigenfunction of Lz is this format. It's always 1 over square root 2 pi and e phi and phi. So that's the eta part. So that's that. And then what we are doing right now, we try to figure out this theta. So it's kind of theta. If we figure out this function, then the job is finished. So that's our job. And so essentially, we start with the the eigenfunction Lz, and now we gradually move on to the L squared, the eigenfunction. So that's the logic which we try to do. Now, so the next job, essentially, we are going to figure out how do we find the theta part. So this is my theta part, which I'm going to show you right now. I call it item number 4. So that is number 3. Number 3 is just a summarize. It is not deriving. It just show you what it look like. Number 4 is going to be show you the theta part of YLN. So theta part is the YLN. So this is the one which we will show you now. And as told you last time, you have 2 ways to do that. So way 1 is directly use the operator L hat squared and solve for this equation like this. And here's the lambda y Ln. This lambda we did not solve for the moment, but you will see in the future this lambda is going to equals L plus 1 h bar squared. But we have not proved it. We haven't proved it. We just showed you what the results would be. So this is what the results you will end up with. Now, in this equation, if you solve that, this is extremely complicated. So this part is difficult. This is very difficult. So this is very difficult to do. So that's why most people never actually try to solve for this, because the equation itself is going to be really complicated. It's not just it's not possible if you do it in the class in this way. It's just very lengthy. Way number 2 is what we use. We use L minus, L plus. These two formula to found, and it turns out this is a much simpler. And I want to show you the key steps, and then we're going to read the textbook. And so that's the key steps. Otherwise, you get lost. So we're going to use these ones. So it has I think 4 steps total. Yes, total 4 steps. And you're going to see me how do we use this. Okay, we're going to do it sure systematically. The first step, all of business is going to prove L plus YLN. Now we're going to prove this guy, which means this operator applied to the spherical harmonics. This itself is also an eigenfunction of Lz. So, in other words, we're going to prove this guy is also an eigenfunction of Lz. So we're going to prove that. Now, I just want you to remember what actually this is happening in the sense that essentially you have a function and you have an operator applying this. Let me show a quick example of what this looks like, what this means really. But it's not directly with the spherical harmonics, because we haven't solved for the spherical harmonic yet. We don't know how large this one is. But what I want to show you right now is just show you what's the logic behind this. And I want to show you one example. Okay? Now, this example may not be the best example, but I will show you something like this. Suppose my operator, of course, the L plus is much more complicated, but suppose my operator like this. Suppose my operator like this. Okay. Suppose this L plus like that. Of course, they are more complicated than that. And this assumption now, if I have a function, let's go to f like this. Okay. What this means is that if f originally is a function, the eigenfunction of Lz, which means Lz, f equals the eigenvalue of like this. So what that means. And then, whatever you apply onto this comes G. So then your Lz, G, this is what happens in prime G like this. So this is essentially what we are doing here. In other words, if f is an eigenfunction of Lz, but this whole things, which means partial f, this whole things, which is defined by, folks, let's erase this. I don't want this to interfere with my thinking. So how this is the eigenfunction, but now I have an operator apply this eigenfunction, which is g. And this g itself is also the eigenfunction of the Lz. So in other words, so f is an eigenfunction, but whenever operator apply on f, this is also eigenfunction. This is denoted by g. So that's the equation like this. Okay. So in other words, this statement just means this part. Okay. That makes sense to all of you? Any questions? Shall there be any questions? So this essentially says if f is an eigenfunction, and another operator applying that function is also an eigenfunction of z. So that is what we are doing here. It's nothing special. That is the called logic we will do. That's step number 1. Step number 2, this is our master equation. This is our master equation, which is so important how entire derivation of the final results is based on this so-called master equation. If we do not have this master equation, then we won't be able to solve for this. The master equation, we use the exact same trick. So we use L plus, so the L plus hat. And then L plus means the ladder operator increased by orbital angular momentum by 1. That's the same idea as the A dagger. You guys remember A dagger here? Exact same thing. If you want to increase or A minus, doesn't matter which way you call that. Essentially, let's put it without dagger. In the spherical harmonics, that's what we're using. That's a master equation. You remember? Upon it, you cannot lower anymore. This guy, I tricked them. I want to apply onto this guy. Did you see this is maximized? So you see my aim is f equals L. So this is the maximized. If you want to increase a little further, Alex, if this is already maximized, if I want to increase this further, what will you get? If this is already a maximum, and you want to increase it further, what you will get? If this is the maximum, if this is the maximum, you want to increase it further, what you will get? If this is your maximum, you want to increase it further, what you will get? Of course, there will be nothing, right? That makes sense? That makes sense? Because you see it's already maximum, but if you increase further, there must be nothing. Nothing. That makes sense? This is the exact same idea. So here is already ground state. You decrease to ground state. Nothing. Because if you have something here, then this must be not a ground state. If you have something here, this must be not maximum. You still keep on going, right? And this is the master equation. And this is so beautiful, which exactly I use this one here. I hope my way to derive this is much simpler, and you can see them very quickly. We'll leave some space here. And now we're going to stop at this point, and we're going to show you systematically how the cap works. And this time we're going to read textbook. Folks, let's go to page 104. So we're going to read it together. Go to page 104. Folks, open a textbook to page 104. Actually, I don't know what the electronic version will be 104. This will be on equation 4.3.11. Let me show you the equation. 4.3.11. That's the equation. Okay, so that's the equation. And we're going to read it together. And I will first ask Toby to read it, and then followed by Cody. Okay. So, 104. Page 104, the equation is L plus L minus, that expression which we have. And which page you found it on the electronic? 6 to 1. Okay, that's different. 6 to 1. All right. So, and on page 105 we read last time, and essentially, essentially this belongs to the next step, which we will do. Toby, why don't you read the equation start with we apply, that starts that one. Yeah, did you see we apply the second paragraph on page 105?
Oh, there it is. We apply Lz+Lz to YLM to obtain that equation. So where we have used Lz+L equals L+Lz plus H bar L plus, and Lz YLM equals MH bar YLM times L plus YLM is a different eigenfunction of Lz, but increases its eigenvalue by plus H bar. This is why L plus is called the raising operator. L plus changes the eigenvalue for Lz, but it keeps the eigenvalue of L squared. This shows a crucial difference between two sets of operators, since the commutator L plus L squared equals 0. The application of L plus to YLM does not change the eigenvalue for L squared. And for 2, since L plus L, the commutator of L plus Lz does not equal 0, the application of L plus to YLM does change the eigenvalue.
Great, thank you so much. Okay, let's read together the equation. Okay, read together the equation. So the equation starts with Lz, L plus. Now, because Lz, L plus, as I wrote down there, it has a commutation. Now, this commutation, I'm going to write on the board. This is quite important. That's essential part. So, essential Lz, here's Lz. So, essentially, what we are doing here is this Lz and L plus has a relationship between these two. So this relationship I already showed you in the textbook. So this you can directly compute it from these functions itself, and this equals H bar L plus like this, and this will equals this amount. So that is when we are using it. So this is from first equation to the second equation. That's in this equation which we utilize it. Now, from the second equation to third equation, what we did was that, did you see you have Lz behind? In other words, this L plus in the front, Lz behind it like this. Did you see the L plus, Lz behind? And this has applied onto YLN. Now, I want you to notice what the trick we are doing here. Folks, did you see the trick? What I did was, in the beginning, I have Lz first and L plus second. Did you see that? But this won't be easy for us. So therefore, what they did was that we swap these two. So essentially, we swap Lz, L plus. Swap them and become this term. Now, you can see Lz can apply that onto Lyn immediately. This was the trick. So this guy just equals MHR, YLN. Because this, the Lym is eigenfunction of Lz. That's why we directly use this function. Now you see, this become a number. So this become a number. So that is what we are doing here. And this is exactly what I showed you on the top. So this, my operator, partial x, in my equation, just L dagger. Did you see that? And they are exact the same thing. This is exactly the same thing. So that's why you can see that equation is completely valid. When we are writing this part, we were struggling, what's the best way to present them? Student, this is the trick. In other words, if you don't know what this L plus applied on YLM, because you don't know YLM is, you don't know it. You cannot put YM close to L plus close to YM, because we don't know the results, because this is what we're still deriving. But we do know Lz applied to this. That's the key. Once you got the third equation, then the last equation is very important. Did you see I have an under brace? Did you see the focus? Did you see focus? Did you see the word focus? So if I want you to pay close attention to the focus on these two ones, you notice that these two are exactly the same, which means it's an eigenfunction of Lz. Because if it's not an eigenfunction of Lz, these two cannot be exactly the same. So that's why you see the coefficient, which is m plus 1 h bar, that becomes the eigenvalue of the Lz. Did you guys get it? Get it? I did. So Alex, did you get it? So that's the key idea. Essentially, we plot on this, and so this is the most difficult part. All right. Once we survive this, and now next paragraph, Cody is going to read this. It's a long paragraph, by the way.
So then now we're ready to find.
Yes, go ahead. Yes.
Now we're ready to find the eigenfunction of L, L squared in the same fashion as equation 2.2.12. A hat phi 0 equals 0 of supporting. Supposing that the eigenvalue of Lz already reaches its maximum value of LH bar, which, for example, of Lz, y double L equals LH bar y, so double L. A further application of L plus 2y double L should produce 0. So that equation, we plug eta sub L of phi equals 1 over the square root of 2 pi L phi into equation 4.3.13 to find an equation for G sub L of phi.
Okay, could you stop here, please?
Yeah.
I want Alex to read the equation 4.3.11. Read all these terms. Alex is very good on this. Can people read it? I really appreciate it. Yeah, go ahead.
L hat plus or minus equals L sub x plus or minus I sub L sub y equals plus or minus h bar e to the plus or minus I phi times the quantity partial with respect to theta plus or minus I cotangent theta partial with respect to phi closed quantity.
Okay, well, very good. Thank you. Excellent. So this is the equation. And Cody, could you keep on reading them, which can be
reduced to that equation.
Yeah, read that equation, please.
E to the I L phi partial with respect to theta of G of L theta plus I cotangent of theta sub theta sub G sub L of theta I L e to the I L phi equals 0, which gives us derivative of G of L of theta with respect to theta, which equals L cotangent theta G sub L of theta.
Okay, thank you. I should read it because start with because.
Because G sub L of theta is a function of theta only, we simplify equation 4.3.13 to the derivative of G sub L of theta with respect to G sub L of theta equals L times cosine theta d theta divided by sine theta, which equals L d sine theta over sine theta, and integrated to obtain the natural log of G sub L of theta, which equals L times the natural log of sine theta, which equals the natural log of sine to the L of theta, or G sub L theta equals sine to the L of theta. This is a special solution where n equals L of the associated Legendre function.
Thank you so much. Thank you so much. Did you see it? So we eventually found what we found is YL. So eventually we found YL. What is YLL is? So this is it's a really great achievement. We found YLL. So this part is just show you that the theta function part. Could you guys write this down? Theta function part. This eventual theta function part is showed you. It should be sine L theta. So this is this is the only one we actually obtained. So that is the one we eventually obtained, this equation. Yeah. Okay, so this is the end result. Let me write this down entirely. Now we don't know the coefficient of this particular function, so I just use the B sub L representing that. The remaining part will contain this part, sine L theta, and e to the I m phi. This L, not m itself, it actually should be L phi now. L phi m. And this part is coming from the LZ part, so which is LZ part comes out. Now here I use n because you have the lowercase m now equals L now, so that's why you can see here I use the L phi instead of n phi, which is I used over where that is here. Instead of here I use n, but now I use L. So this is the maximum one which we have. Okay. Once you survive this, then the remaining steps become simpler. And that is so-called step number 2, which eventually we found this. Now, one more step, because we found a 1 now, which is good, which is really, really good. And now we're going to find step number 3. This is step number 3. Find the remaining y, L, m. So this time, the m is not equals to the m now. So it's kind of remaining part. That's why I call it remaining, because some of these may not be the maximum. So this part is called the remaining part, which I'm going to show you now. Okay, so that is the remaining part. The job is the following. This job actually relatively easier. What we would do, we do the following. We only found YL, so that's it. With nothing else, we found it. Now what we do, you see, we do the exact same trick. You remember this guy, L plus, is increased that. Do you see that? This one actually decreases. This will produce y, L minus 1. So if we apply the ones, you will get L minus 1. And we will prove this shortly. If you apply it onto y, L minus 1, it will reduce to L minus 2. And that's what we're going to lower in our pair. So it's just lower the ladder, keep on going, and all the way until you get y, L minus L. So you see, all these remaining spherical harmonics can be derived. Start from this guy and do once, you get this, one twice, and then at the end you get y, L minus 1. So that eventually you're going to get this relation. So, and now we're going to read section. So we're going to read a section in 4.3.4.1. I use these so many small sections because I found other books is going to skim over so quickly. Students did not get understand. You see, that's why I have some questions. And the publisher asked me, "Do you really do so many stuff?" And I said, "We do," because that way you can show all the details. The student will really appreciate. So this time I'm going to ask Cody to read it first instead of Toby. Cody, this is on page 106. Page 106, and I shall probably similarly, maybe you have a few lines down here. 106. Cody, why don't you get started with this to obtain until you read it until equation 4.3.17. Okay. Yeah.
To obtain, do you want me to read the equations too?
Yes, please do so.
To obtain the rest of the eigenfunctions, we go back to 4.3.12 and 4.3.
Let's go back to 3.12. Folks, let's go to 3.12. So 3.4.12, and that's the equation which we derived the spherical. And one of the other ones, it says have 10. That's a 10, which is the Lz equal that amount. Now, we will use the L squared. That's 4.3.10. L squared equals L plus 1. We haven't derived this yet. But we will use the results now. And we will show you in the next step, we never try to use this result from any other unknowns. We will derive independent of what we derive here today. So that's very important. So we're not just like know the results, you plug it in and get a result. Doesn't make any sense. We'll start from scratch and we'll show you this one. Okay, keep on going, please.
L sub z, L plus y lm equals m plus 1 h bar L hat plus y lm. And then Lz of y L m plus 1 equals m plus 1 h bar of y sub L m plus 1. And compare these terms, and compare the terms in the square brackets in the previous two equations. We conclude that these two terms must equal to each other, up to a constant c. L hat plus y lm equals c lm.
Okay, thank you so much. Any question up to this point? Any question up to this point? So, any questions? We just said compare the term in the square brackets. In other words, just compare the first equation in the square brackets and the second equation in the square brackets. Because the left-hand side of square brackets and the right-hand side of square bracket, and so that's the main reason we want you to see those ones. So they must be exactly the same. So, you know, it's when you have these two. So that is just compare the square brackets. So these two square brackets must be exactly the same. And any question on this one? Okay, no question. All right. Actually, why don't you continue on this?
This shows that if YLM is known, we can generate a new eigenfunction by applying L sub plus to it. So first we need to determine C sub Ln. We take the Hermitian conjugate of equation 4.3.17. YLM star times L minus equals C star Lm times YLM plus 1 star.
Great. Hold on 1 second. Toby, did you see when we do the Hermitian conjugation? Did you see the operator in the beginning? L plus is in the front. Did you see that? But next equation, when you use the Hermitian conjugate, this L plus actually becomes the second and next one. This is what you did. What we did is just a rotation of these two operators. Now the second one, which is the equation, doesn't matter because these are just functions. The right-hand side is just functions. That's why I only have a star. So that's a very important that you asked me question last time. And then you can see when you multiply by those on the front, and you will get the following. Alex, could you read and multiply by this one? Starting with the and multiply equation.
And multiply equation 4.3.18 and equation 4.3.17 from left to right to get conjugate of y sub lm times L sub minus hat times L sub plus hat. Y sub lm equals the absolute value of C L's sub lm squared. The complex conjugate of y sub L comma m plus 1 times y sub L m plus 1.
Keep on going.
Where we have used L sub plus dagger equals L sub minus hat owing to L sub plus or minus hat equals L sub x hat plus or minus I L sub y hat.
Great, thank you. So Toby, now you see why the L dagger equals negative of L is because L plus minus equals Lx. If you apply the complex conjugation on this, Lx stays the same, Ly stays the same, but the I will be changed sign. That's why the plus minus is swapped. That is the main reason why we get that equation. And when I was writing this, because a lot of books, they just skip through this very quickly. I don't want to show all the details actually you can have. So that's why I like this. Okay, Cody, could you read on? I will focus on.
Our focus is on L minus, L plus, y ln. Note that L squared equals L squared x plus L squared y plus L squared z equals L squared z plus 1 half L plus Ly plus L minus plus L minus L plus, because L plus L minus equals 2h bar Lz. L plus L minus minus L minus L plus equals 2h bar Lz, or L plus L minus equals L minus L plus 2h bar Lz. We have L squared equals L squared Z plus L minus L plus H bar LZ. Example is L minus L plus, which equals L squared minus L squared Z minus H bar LZ. Then L minus L plus YLM equals L times L plus 1 minus M squared minus M H bar squared YLM. Where we have used equation 4.3.10, equation 4.3.19 can be simplified to that equation.
Okay, great. Thank you so much. So that is what we did. Now, tell me the next paragraph that you're going to read. This is what you wanted before. Keep on reading that, please.
We integrate both sides over theta and phi. You want me to read that?
Yeah, read all the things.
The integral of the complex conjugate of y sub Ln times the quantity L times the quantity L plus 1 plus quantity minus n squared minus n plus quantity h bar squared times y sub Ln times sine theta d theta d phi, which equals the absolute value of c sub Ln squared times the integral of the complex conjugate y sub L n plus 1 times y sub n L n plus 1 times sine theta d theta d phi.
Okay, hold on to this. So this entire equation, Tobin, this entire equation is really, really interesting. In other words, you saw you have such a long integration equation, but in the direct notation, you will see something like this. In other words, in direct notation, it's just this notation. The exact same thing that one did. So you see that's much simpler. But there you have a d theta, d phi, a whole bunch of the things. Yeah. Keep on going, please.
And use the orthonormalization relation in equation 4.3.16. They get c sub Ln equals the square root of L times quantity L plus 1 post quantity minus n times quantity n plus 1 post quantity each bar, where we choose a real c sub Ln. So finally we have L plus times y sub Ln equals the square root of L times quantity L plus 1 post quantity minus n times quantity n plus 1 post quantity h bar y Ln sub Ln plus 1, and then L minus y sub Ln equals same, but n times quantity n minus 1 post quantity h bar y sub Ln minus 1. Where the derivation of the second equation is given in the following exercise, we can find the rest of y sub Ln from these two equations.
Great, thank you so much. Folks, so let's go back to equation 4.3.16. So just the last page. Did you see, this is all these spherical harmonics, they were orthogonal to each other. But the sine theta d phi, did you see sine theta d phi? So this part is quite important. In some books, they use called the volume angle. So this is usually, in other words, some textbook, you guys write this down, some textbook, they use d omega. This d omega is the d theta, d sine theta, d phi. This they usually call a volume angle. So you have a volume angle, it's an integration like this volume angle. You not only integrate over the theta, also integrate phi. So this is called a volume angle. They usually use a d phi. And in our book, we decided to just use the this entire expression instead of the other ones. That will get. Okay, so that's the entire thing. How do we do the calculation? All right. So this is my third step. So this third step, we found the remaining part. So all these are the remaining part can be calculated recursively. So this you call it recursive relation for y, L, N. So the equation that you saw there, the L diagonal becomes L. That's called a recursive equations, and that's usually you can use that. The last step is called step number 4. Step number 4 is we find eigenvalue. The eigenvalue of L squared. You remember we already used this results, but we're going to prove this. So this is L squared YLN is going to equal L plus 1 and YLN. Sorry, H bar. We'll write this one. H bar should be here. So the eigenvalue is this part. That's eigenvalue itself. And this eigenvalue is very strange. Before I show you how do we derive it. This very strange. Even YLM depends on M, but the eigenvalue does not. So in other words, even the YM itself depends on M because clearly it's a function of M. But the eigenvalue itself is not. So this is something which is quite unusual in the sense that how you can have a function without actually affecting this. This is the main idea of the common state. Okay, so we're going to read on page 106. This time I'm going to ask, I shall read first. Starting with equations 4.3.21. No. The start from equations, eigenvalues of L, section 4.3.4.2. 4.3.4.2. Yeah, got it.
Equations 4.3.21 and 4.3.22 make it possible to commute the expectation values of Lx, Ly, Lx squared, Ly squared, and Lx squared plus Ly squared. Here we use them to find the eigenvalues of L squared, but there are two ways to obtain them. One is to use the ladder operators, and the other is to apply L squared to Y double L with the following.
Okay. Yeah, that's good. And I want Alex to read the second paragraph, please. Alex, read the second paragraph. We rewrite.
We rewrite L hat squared in terms of L sub plus hat, L sub minus hat, and L sub z hat. L squared hat equals L sub x squared hat. L sub x hat squared plus L sub y hat squared plus L sub z hat squared equals the quantity 1/2 times the quantity L plus hat plus L minus hat closed quantity squared plus open quantity 1/2I times open quantity L plus hat minus L minus hat closed quantity squared plus L sub z hat squared equals 1/4 times open quantity L plus hat squared plus L minus hat squared plus L plus hat L minus hat plus L minus hat L plus hat closed quantity minus 1/4 open quantity L plus hat squared plus L minus hat squared minus L plus hat L minus hat minus L minus hat L plus hat closed quantity plus L sub z hat squared equals 1/2 open quantity L plus hat L minus hat plus L minus hat L plus hat closed quantity plus L sub z.
Great, thank you. Yeah, thank you. And I want Cody to continue the next one. Using on page 108. Yeah, page 1.
Using L plus L minus equals 2H bar Lz to change L plus L minus to L minus L plus 2H bar Lz, we obtain L squared equals 1/2 L minus L plus, which is 2H bar Lz plus L minus L plus close parenthesis plus L squared z equals H bar Lz plus L minus L plus Lz squared because L plus y double L equals 0 and Lz y double L equals LH bar h bar squared L plus L squared h bar squared close parenthesis y double L equals L parenthesis L plus 1 close parenthesis h bar squared y double L. So the eigenvalue of L squared is L parenthesis L plus 1 close parenthesis.
Thank you so much. I'm sorry, so many letters.
That's okay.
Yeah, okay. I think everybody enjoyed reading these letters now because you want to be. You see, we never use these recursive equation we used before. We never use it, except the when L plus you see y, this guy. Except this guy, we used it, right? We only use this relation. We never use the other ones. That's why the entire derivation is self-consistent. I struggled on this part a lot because some books are just like hand waving, oh, here's the results. But how this logically get is still, there's no kind of using the known results to derive a result. Not making any sense. You only count the results. So that is why. So this is the key equation which we want you guys to remember. Now, so once we got these ones here, and then we get all these equations, eigenvalues, eigenvectors, and we are ready to look at what actually these means, essentially what they are being useful for our purpose. So this part is essentially add a new dimension to our understanding. So this new dimension, which is very important, and in other words, the good news is that now the main portion of our results is available for us. And now we're going to enjoy this part a little bit. So the most complicated section already passed. And now when the new section comes over, it's make things a whole lot simpler. We purposely added one section, which we call understanding orbital angular momentum. We spend a lot of time to derive this, but we want to understand what actually is happening without skip them because they are so important. What they are actually. So this is one thing that I think we are very proud of. This particular section is very important. Let's look at the physics first. So the physics part, and which is quite important. So the first. And we will show you that within the this is the eigen function Ym, the quantity L dagger, this expectation of L dagger squared, and Lz, these are all well defined. When I say well-defined, what I mean there's no uncertainty. No uncertainty. Everything is certain. There's no uncertainty. In other words, there is no uncertainty whatsoever. These values are well known. Because this is the eigen, because they are because Ylm is an eigenfunction of L and Lz. And their value is known. The value for this one here is L plus 1, h bar squared. And the value here is n h bar, like this. So that is the value itself. And my n there is going to take plus minus L minus 1 all the way to 0. So essentially, from negative L to positive L, you keep on increasing in this way. So that's the n. And this is called a magnetic quantum number. Magnetic angular momentum quantum number. So it's called a magnetic angular momentum quantum number. So sorry, it's a little bit long words, but that's what we're using it. If you simply L part, that will be called angular momentum quantum number. If M will be magnetic angular momentum quantum number. The reason why we call it magnetic is because this guy will be affected by the magnetic field. That's a Zeeman fact. So you guys all did the Zeeman experiment. That's a Zeeman effect is connected with this L here. So you have a different L, and that's why L plus minus 0. So if L equals 1, you have a minus 1, plus 1, and 0. And this is the one which we will discuss on the next one. And the second one, we'll talk about the other operators. So we're out of time today, so see you guys on Wednesday. And Wednesday, we will first, we have a quiz on Wednesday. Make sure it's going to cover similar materials, including mainly on this in this particular chapter, and some portion maybe for the last chapter as well. Okay. All right. Any questions? Sure. All right. If not, I'm going to close this now. Stop this. I will return the homework to you guys on